All right. So we are in class number 20. And in the last class, we were talking about introduction to operating system. Today, we will be looking at its structure. So operating system structure, what are some of the things that go on in a layered operating system. We will talk about system calls. We will talk about a virtual machine, the concept of the virtual machine. And then we'll talk about how you can create several processes. Why would you need to do that? And how do you actually code that in? All right, so let's start with uh, motivation for a structure. So why do we need a structure in the first place? Well, the answer to that is there are many services that are being managed by the operating system. For example, executing processes coming from many users. I need to manage that. Who gets to use the resources of the CPU when and how much? I need to manage that. OS needs to do that. IO operations, right? So communication and monitoring the interrupts, completing the input-output operations. All of those things are being handled by the operating system. Communication, and this communication could be between devices in the computer system, or it could be between processes, user-created processes. How do I manage that? Well, I may need to program some pipes to allow for inter-process communication. That is also a service managed by the operating system. Allocating or deallocating physical resources, right? Space in memory. Is a process getting a CPU or not? Is a process able to communicate with a particular device driver or not? So allocating physical resources to processes is also managed by an operating system. Protection and security. From what? Well, protecting good users from bad users, as well as protecting the operating system from the bad users, right? So all of that goes into the as a service that has to be managed by the operating system. Also, error detection. Suppose I'm writing something to memory, and during that data transfer, if an error has occurred, then the operating system needs to do error detection in that. Also, accounting. For example, which how many processes are right now being running, how many processes are available to the system, um, what percentage of the CPU resources are being utilized by a certain process. So all of that accounting information also needs to be managed by the operating system. And as you can see, this list is pretty long, right? And we also need an interface. We need to interface with the system as well. Now, what happens is, because we have so many services that are being provided by the operating system, and if you think about writing this very large and complex operating system, it would be impossible to do it at one layer, in one module, as one component. So what you do is you you divide it up in a structure form, right? So you give it some hierarchy, you give it some modular approach, right? So that you are trying to isolate services into certain groups, into certain modules. So if you had all these services that are being managed, just think about the size of a general purpose operating system, such as a Windows operating system. That would be very, very large. And hence, we need a way to structure it. And there are several approaches about how you can structure an operating system. And as you may imagine, early designs were monolithic and they were simple, which means that there was no structure at all, right? Everything was treated equally and it was at one layer, right? There was no hierarchy built into it. There was no modular component to it, right? There was no structure at all. And it was a big problem. Just think about it. If there is an error, or if a certain service provided by the operating system is not working and it needs a fix, where are you going to look, right? You're not going to know which particular module you need to look into, because there's no modular approach there. There's no structure there. So we need a way to organize interfaces between the operating system services. So that's what happened later. Later on, there were ideas to organize certain interfaces between operating system services such that each layer or each module could be responsible for a certain limited number of services, right? So that's where we are isolating, okay, layer 1 does this, layer 2 does these other jobs, layer 3 does these other jobs, and so on. So the first such approach was layered structure. And we'll talk about the layered structure in just a minute. There were some modern approaches to this, which was microkernel, modular structures, and hybrid structures, which can be a combination of microkernel and modular approaches. What does microkernel mean? Well, as the name suggests, it's a microkernel, a small kernel, which means that only the kernel is made very, very small, and you push out the operating system services to the user space, right? So you're making the kernel very small, and you are pushing out the services to the user space. That's a microkernel structure approach. Modular is very similar to layered, but in modular there is no strict hierarchy built into it, right? Modular just simply means services that are modular. Layered means one above the other. So there is a hierarchy built into the layered structure. Hybrid means a combination. The good things from different structures could be borrowed to get the hybrid structures, right? So it's a combination of many different types of OS structures. All right. Now let's take a look at the layered operating system structure. As you can see over here at the right, you can see layers like peeling off an onion, right? Like there is a layer 0 right in the middle here at the center, which is the hardware. Of course, the bottommost layer is going to be the hardware, which is being shared by different users, right? So at the topmost layer, you have layer N, which is the user interface, right? So the users are sort of sitting way outside of this, and they're trying to access layer 0 maybe to get some physical resources. And for that to happen, they have to go through several layers, N layers shown over here, well, N plus 1, including 0 for hardware. But at each layer, there is a certain service that is being provided by the operating system. Now, because it's large and complex, we need a good way to build them. And one way is doing this layer. The idea is build them in layers. So it is somewhat modular, right? Because it's still layer 1 is a module, layer 2 is a module, layer 3 is a module. However, there is also a hierarchy built into it. So it is somewhat modular, but it's not completely modular. Completely modular would be layer 1 and layer 2, or module 1 and module 2 and module 3, something like that. There's no hierarchy there, but there is still isolation of services provided by the OS. A layered structure is somewhat modular there. There's still isolation, but there is another thing that that could be an advantage, or you could also spin it as a disadvantage over here. Let's talk about it a little bit later. Now, with this layered approach, what we gain is portability. As you can see, there is the hardware that sits over here. I can take this operating system and port it to a different hardware, and it would work exactly the same. So this allows me to port operating system onto different set of hardware. And each layer is sort of using this divide and conquer philosophy, and that allows each layer to be simple. And another advantage that you get is, if there is any error that needs fixing at a particular layer, then we know exactly where to look for that error and fix it, because now we have made it layer 0, layer 1, layer 2, and so on, right? So if there is a certain service provided by the OS getting impacted, we know where to look for. So that's sort of an advantage of this layered approach. Now, by doing this layering, we can talk about two more things here, which is, first one, higher layers are written in terms of lower layers. You see, when I say layer 1, I'm writing layer 1 in terms of layer 0. And when I'm writing layer 2, I'm writing it in terms of layer 1 and layer 0. In other words, layer 2 will be able to use all the services provided by layer 1 as well as layer 0. But layer 2 cannot use the service above it, right? So layers cannot use the services provided by the layers above them, but they can certainly use the services provided by the layers below them. Now, lower layers can hide details from the higher layers. So for example, layer 1 can hide the details from layer 0 and so on. But so if I say that higher layers can use the services of the lower layers, there is a problem. There is an issue that could rise because of that. And that issue is, what if it is the other way around? What if layer 2 needs a service of layer 3? What then? Right? That's an issue. So that's a problem. The problem is that service cannot use service at a layer lower layer. Service at a lower layer cannot use service at a higher layer above it. So that's a problem here. Now, if you look a little bit deeper into this layered operating system structure, way at the top, we have the users, right? So all the way at the top, we have the users, and I can also put the hardware over here, right? Hardware is all the way at the bottom. And between the users and the hardware, there are sort of two spaces. One is the user space, and sort of this is user space, which includes the users, and it includes shells in which you can type in commands and you can run your compilers are over here, etc. Right? So all these are user processes that are essentially not privileged, right? Like user space is not privileged a space. And whenever you want to get privileged services, then you would need to use system calls to go into the kernel space, like we talked about in the previous one, by adjusting the mode bit in the dual modes type of OS. Then you can go to the kernel space, do the privileged operations, and then eventually come back to the user space. So way over here, you have your user space interested in running applications on top of a kernel, right? And the interface is the system call interface to the kernel. And the kernel itself is sort of divided into two layers itself. One is signals and terminal I/O, file system support, CPU scheduling, and virtual memory. All of that are services that will eventually interact with some hardware controllers, right? So hardware has hardware controllers, and the device driver interface allows these services to execute on those hardware controllers. So including terminal controllers, controllers for disks and tapes, or memory controllers. So this is sort of the system call interface to the kernel that is sitting right over here. Now, how do you go from the user space to the kernel space? Well, that could be an interrupt, right? That interrupt could be a software interrupt or a hardware interrupt. So that's how you would go down to the kernel space. Now, let's spend a little bit of time talking about virtual memory. Virtual memory, not virtual memory. This is virtual machine. So it's still a VM, but this time it's a virtual machine. So what is a virtual machine? You guys might have heard this term virtual machine several times, right? And the technology that it uses is virtualization. What is it? Right? It simply allows operating systems to sort of run as applications within other operating systems, right? So virtualization is what is allowing OS to run as application on other operating systems, right? And I'm sure if you own a Mac, most likely you have had to do this, where you have had to uh, create an environment for a Windows operating system on your Mac machine using some sort of a virtual machine, right? So what is it now? If you take a look at this picture over here, what do we have? We have two virtual machines. I'm going to circle them over here. There's virtual machine 1 over there, and then there is a virtual machine 2 over there, also called as guest operating systems, right? So this is the VM1 and VM2, also called as guest OS. Yes, operating system. Now, on each of these virtual machines, you have certain applications that are running over this guest operating system, which uses certain hardware resources. But the hardware resources are abstracted from the real hardware resources. These are including CPU, memory cards, network interface cards, or hard disks, right? So virtual machine 1 thinks that I have access to all these resources. And virtual machine 2 also thinks that it has access to all these hardware resources. So suppose you have a server which has several cores, a lot of RAM, a lot of disk storage. Then what you can do is you can take advantage of that very resourceful machine by running several virtual environments on a virtualization layer, right? So, something needs to be an intermediary between all those resources and the guest operating system, and that's what a virtualization layer makes it possible. The virtualization layer is hosted on certain architecture. In this case, we have the Intel x86 architecture. So that's sort of the concept here, right? So it's essentially saying I have a lot of resources available to me at a server. How can different operating systems sort of access these resources at the same time, right? So there is some time sharing going on. Not just time sharing of the resources is also going on. Hardware resources going on through the use of this virtualization layer. So that's your hardware level abstraction. So it allows for that extra level of indirection. It decouples your hardware and the operating system. It enforces isolation. What this also means is that you can have different operating systems take charge of the same set of physical resources, right? So that's also giving you that um, cost saving. You guys see that? Now, what goes into the virtualization layer? One thing, by the way, virtualization layer is also called as a virtual machine monitor. Let me just VMM, virtual machine monitor. So sort of this last point is sort of summarizing the goal, right? So to multiplex physical resources across several virtual machines. Now let's talk about the hypervisor. Virtualization is simply creating a software based or a virtual version of something. It could be computer storage, or it could be networking servers or applications. And the virtualization is what is making this possible, right? So what makes virtualization feasible is the hypervisor. It is the software that is installed on the computer hardware, creating that virtualization layer. It acts like a platform for the virtual environments to be created on. So it's sitting right here, right? So it's a software layer on which you are creating these environments for different virtual machines. It is responsible to manage and share the physical resources between the different virtual machines. It is essentially pulling the resources from the actual physical server and allocating them to the virtual environment. It could be on a time sharing basis, a time sharing or time multiplexing that is happening over there. There are essentially two types of hypervisors. Type 1, also called as a bare metal hypervisor, is directly installed on top of the physical server. So that's where you have the hardware, and on top of the hardware, you have the hypervisor installed. I can draw that over here as hardware here. And on top of that, you have the hypervisor. So that's called a bare metal hypervisor. And their examples include VMware, ECSE, Microsoft Hyper-V, open source KVM. All these are sort of type 1 hypervisors. Type 2, also called as hosted hypervisor, has an host OS in the middle. So essentially over here, what we have is hardware. On top of the hardware, we have an operating system, or the host operating system, and the hypervisor is installed on top of the host operating system. The host OS is sitting between the hardware and the hypervisor. Examples: Oracle VirtualBox, VMware Workstation, and at some point, many of you must have had that situation where you wanted Linux on a Windows machine and so on, and for that you may have come across some of these names. Now let's switch gears and start talking about system calls. What are these? Well, these are providing an interface to the services that are made available by an operating systems, right? So these are tools essentially that are written in the form of routines written in C, C++, or even assembly language. So it could be assembly, it could be C, it could be C++, routines. And what are they? They are mechanism for an operating system to provide services. There are three methods to pass parameters between a user process, and an operating system. One could be in the form of registers, other could be as a block or table in memory, or we could be using a stack and pushing data and pulling data from a stack to pass parameters from a process to the operating system. Again, system calls are necessary for you to go into the kernel space to be able to execute some privileged aspects of an operating system. If you want, and that is essentially triggered by interrupts, right? So it's equivalent to a software interrupts system call. And then we are talking about how a user process can pass parameters to the OS. It could be form of registers and block and all of those things that are listed over here. We will be taking a look at some system calls in detail today, but let us first talk about what are the different types. So we have over here 6 different categories in which we can have system calls. One is process control, file manipulation, device manipulation, information maintenance, communication, and protection. So when you look at process control, these are system calls that are specific to user processes, right? So for example, if you want to end or abort a particular user process, load, execute a process, create a new process, terminate a process, wait or signal event. So suppose a process is waiting for another process to complete. A process is waiting for a certain IO operation to complete. Those are system calls that are relevant for that. Allocate or free memory for a particular process to get executed. That is also part of the process control type of system calls. Next one is file manipulation or file management. In this, you have system calls such as create or delete a file, open or close a file, read and write or seek in a file. And then you can also get or set file attributes, who can write to it, who can read from it, and so on, right? And then the next set of type of system calls are device manipulation. Can I, request or release a device, read and write and seek to a particular I/O device, get and set device attributes, logically attach and detach. As opposed to physically attach and detach, you usually mount and unmount a device when you physically attach to it, right? That's operating system recognizing the device, also called as logically attaching a device. Now, in terms of maintenance, information maintenance, we could be doing get or set time system call. You want to change the system time, you got to use that system call. Get or set date, get or set system data, process or file or device attributes. All of that goes into information maintenance. Then we have system calls that are communications specific. So how do you create and delete a connection between processes? Send or receive messages between processes? How can you share information, status between processes? And then attaching and detaching remote devices on a network. All of that goes into the communication type of system calls. At the end, you have protection, in which you can set or modify permissions. Here is a list from the textbook giving you, Windows as well as Unix system calls that fall under, some of them that fall under each of those 6 categories. So for example, in the process control type of system calls, we are going to be looking at fork, exit, and wait Unix system calls in a little bit of detail. Note that each system call here could be different, right? So for example, fork creates processes in Unix, but it's a different function in Windows. In Windows, we would have to use the system call called create process. And exactly like that, you have all of these system calls here. For reference, we will be focusing on the first 3 Unix system calls in our lecture today. We'll be spending time on maybe open, read, write, close later on. We will also be looking at pipe when we talk about inter-process communication. But I think that is sort of where we will stop there. Now let's take a look at process state diagram. This is essentially a view of the life cycle of a process, right? So a user process will go through many different states during its lifetime. When you, and these are all states, right? So these are all states. When you create a new process, maybe you used the Unix system call fork, that creates a new process. But it doesn't mean, so create doesn't mean start working on it, right? So just create process or fork, that is a process that is new, right? So the state in which it is in is called the new state. It is right now, it is created. What happens is it gets admitted to a ready state, which is essentially managed by a ready queue. When the new process gets admitted to a ready queue, over here, it is essentially waiting for a CPU to work on it, right? So it's the next step for a process is to start execution. But it is not going to start execution until there is a CPU, there is a processor available for it. But when it is, a scheduler dispatch is going to assign a processor to it, and then it is going to go into a running state, right? So you've got a newly created process that it gets admitted to a ready queue. So it's ready to get a CPU now. Then the scheduler dispatcher sort of assigns a CPU to it. It goes to a running state. Now it is being executed. And suppose it gets finished, right? Now it's done. It's done running. The process is complete. Then it will exit to the terminated state where it will end, right? So that's a complete cycle. Start here, go, I'm ready for a processor, assign a processor, work on the process, gets terminated, right? So that's your 4 states that are very straightforward. However, when a process is running, we could have an interrupt. And when there is an interrupt, we go back to the ready state, and again we are waiting for a processor to be assigned. So we are again waiting for that scheduler dispatch to assign as a processor. Another thing that could happen is, if we are in the running state for a particular user process, we could be waiting for certain IO operation to complete or a certain event to happen. Then we are in the waiting state, right? So in the waiting state, we are essentially waiting for some IO to complete, input output operation to complete, or a certain event to happen. Once we are done with that, once that is complete, we go back to the ready state, and then we are again saying, okay, do you have a processor for me so that these instructions that I have in this process can be executed. So this is sort of a life cycle of a process, also called as the process state diagram. And we will be referring back to this a little bit later as well. Also note that these names are going to be varying across operating systems. And we all know, what a process is, right? Like a process is not a program. A process is a program in execution state. So we are talking about a process here. All right. Next, we talk about the process control block. So this is going to be something similar to the device status table that we saw for asynchronous IO that we looked at in the previous class, right? So each process that is present is going to have a process control block. And each process control block will have many pieces of information that are associated with that specific process. So for example, it could include process ID, PID. Usually we see it as PID, also called as the process number. It could have information about the process state. Is it in the new state? Is it in the ready state? Is it in the waiting state? Is it in the running terminated state? Which of these 5 states is the process in? That is going to be part of the information that is present in each PCB, right? This is specific for each process. Then it could also have the program counter information. What is a program counter? Well, it is a register that contains the address to the next instruction to be executed in that user process. So that information also part of the PCB. It could also include CPU registers. So these could be stack pointers. These could be general purpose registers. All of those are also part of the PCB for that particular process, right? CPU scheduling information. So this could include things like priority. So if a process is higher priority versus lower priority, then how it gets scheduled by the scheduler dispatch changes, right? So that is going to be relevant to the CPU scheduling information. So priority can go in that. Memory management information. So something like, so let me just write these down. Priority could go in here. Then base and limit registers could go in here. The base and limit registers are for each process that we saw in the previous lecture. That information could go as memory management information for a process in the PCB. Then we could have accounting information. So for example, how much amount of CPU is being used by a particular process. What are the different job or process numbers that are involved. All of that could also go in accounting information. Then also we have the IO status information. So for example, if a process is doing some input output operations, that status of those IO devices also part of the PCB. And because process state is part of the PCB, as it changes state from new to ready to running to waiting and so on, the PCB will be updated. I suppose over here we can mention one more thing, right? So new to ready to running to terminated, that is sort of a open loop, right? Like that is going to happen, start to end of a process lifetime. Or you could be doing this, right? You could be sort of doing this, and eventually you may end. All right. Next, let us talk about how do you keep track of PCBs. Now, to meet the objective of multi-programming, which is to have some process running at all times to maximize what? To maximize CPU utilization, or to meet the objectives of time sharing, which is essentially to switch the CPU among processes as frequently as possible. The process scheduler is going to select an available process for the program execution on the CPU. Now, this essentially involves maintaining and scheduling of jobs from queues. Now, we have three different queues that we are going to talk about: a job queue, a ready queue, and an IO device queue. A job queue essentially is going to consist of all the processes in the system. A ready queue is different. A ready queue is going to consist of all the processes that are residing in the main memory and are ready to get executed. So they are just waiting for a processor to be assigned. The IO device queue contains the list of processes that are waiting for a particular IO device. Now, the queue itself is a stored linked list. It's a linked list where the head contains the pointer to the first process control block in the list, and the tail is going to contain the pointer to the last process control block in the list. And each process control block will have a pointer to the next process control block in the queue. So you have a ready queue here, head contains the pointer here, and then PCB1 has the pointer to PCB8. Process control block 8 has a pointer to process control block 25, right? So that's your ready queue. So as the scheduler dispatcher is going to be looking at this queue, it's going to say, all right, where should I go next? PCB1, where next? PCB8, and so on. So the process control blocks are going to go from one queue to the other. All right, let's spend time talking about how do you create processes using this Unix-based system called fork. Some of your homework problems are using this particular concept, and it's a very interesting concept of creating multiple new processes, right? So fork is a Unix system call to create processes. I have one, I can fork into two, and now I can fork into many more if I have that fork system call even in the child processes. Let's talk about this in a little bit of detail with examples and code and all of that, right? So a process, there's a user process, executes a fork system call to create a child process. A child is essentially a clone of the parent process, right? So you have a parent process, and if it executes a fork system call, it creates a child process. A child and a parent are exact replica of each other. They could be different, and we'll talk about that, but they are at the beginning clones of each other, right? So the original process is called the parent process. The newly created process is called the child process. I hope you guys are all okay with why we need process creation, right? You're creating new processes so that you can work on more things at once. This is essentially tying all of our, the degree of multi-programming and the graph that we saw between degree of multi-programming and CPU utilization. You want to increase CPU utilization, you create new processes, thereby increasing the degree of multi-program. Right? So you are having something to do for the CPU at all times. That's the goal. Right? So the child is going to be identical to the parent, like I said, a clone, but with one exception. The exception is that the return code is going to be different. The return code for a child process is 0. This is something important to note. But at this point, you guys just should be making a note of this statement. What I'm hoping is that when you see an example, you will relate to this a bit better. The return code for the child process when there is a fork system call is a 0. The return code for a parent process is the process ID of the child process. That's how they are different. The return code for a child is 0. So if you look at the return code and it is a 0, you know it's a child process. The return code for a parent process is a non-zero integer, right? So PIDs are always integers. Process ID is always an integer. The parent process, the return code is going to be the process ID of the child it just created. So let me highlight also in, say, blue. So for a parent, it is child process ID. For the child, it is 0. Now, the parent and child may execute concurrently in parallel, or the parent may wait for the child process to complete. It is up to the process to decide that, right? So now there are sort of two processes that are concurrently getting executed. One is the child, one is the parent. They both have the same program, right? They both have the same instructions. They are sharing the memory space as well. But parent could wait for the child to complete. And there are certain other system calls for that. What is the system call for that? Let me go back and take a look. Wait, right? So if I want that parent to wait for a child to complete, I'm going to be using a wait system call for that. All right, let me come back here. Okay. Next, the child may be duplicate of a parent. So by default, it is that. Child process is a duplicate of the parent process. Same program and data. Or by using an exec system call, we can actually replace the child process with a new program. So we'll also see an example of how we can do this. We can actually replace the child process and load a new program into it by using a exec system call. A few more details about this fork system call. Suppose you have a parent, right? So some parent process is getting executed all the way over here. It has a process ID, and we are denoting the process ID as X for that parent process. I'm going to pick some integer for this, maybe 137, right? So I've just assigned X the value of 137. Arbitrarily, I've picked some integer as the process ID of the process parent process. Then as we are going through the instructions in the parent process, at some point there is a fork system call that happens in the parent process. And as soon as the fork system call gets executed, we are going to have two processes that are going to fork out of the parent process. One is the parent itself, the other is the child process. Now, how do you identify between the parent process and the child process? It is going to be about what they return. Where are they returning the value? They are returning the value in I. So I is going to be 0 for the child process. The return code for a child process is 0. So I becomes 0 in the child process. But I is going to be something else in the parent process. The return code for the parent process is going to be the process ID of the child process. So whatever y is, right? So if y is say 528, then that's what is going to get returned by the parent process. So I hope you guys see the difference here. The way you know it's child is by looking at the return code. If it is 0, then you know it's a child process. If it is a non-zero value, then it is a parent process. Now, the process ID of the child is y, a new number, right? Doesn't have anything to do with x. It's a new number. Process ID of the parent is still x, right? So this is the same as before. You guys see that? Maybe a different. All right. So parent process getting executed. You have a fork system call, forks into a child and the parent. Now what happens after that, right? What happens after that is you essentially have two programs exactly the same. They are ready to execute the instruction right after the fork system call in both of them concurrently. That's what is going to happen next. So after the fork, right, there are several things could happen. First thing is we could actually replace the child process with a completely new program, completely new process by using the exec Unix system call, thereby transforming the child process. So we'll replace the process's memory space with a new program. That is possible because now they are the same, right? So child and process are the same. What if I wanted child and process to be different? Well, use the exec system call to replace one of the processes. Another thing that we could do after the fork is one process can wait for the other. So typically the parent process can wait for the completion of the child process. Again, a user process option. A process can kill itself by doing an exit, right? So if you have an exit system call in either the parent or the child, then you're essentially terminating that process. One process can kill or abort another if it has the privilege. So if the privileges are set appropriately, then a parent process and a child process could kill or abort the other. And then we can also exchange data, that is communicate between parent and child using inter-process communication through pipes. We will look at pipes later on. Let's take a look at how things change when you start executing a new code in the child. Again, we are starting off with the parent process here. We have a fork system call in the parent process. This guy or down. So let me ask you guys this. What is this? Is this a parent or a child? And then I can say the other one is going to be parent or child. So which one is this? Right. So this is going to be parent. The reason is its return value I is non-zero, right? So the moment you see I is y, you know that it is a non-zero integer, a non-zero value. Of course, it's going to be a parent process. So that's one way. And the other is I is 0 over here, which indicates that it is a child process there, right? So now in the child, what we are doing is we are using another system call called exec. By using that, we are changing the we are actually dumping the parent program, and we are putting a new process into it. Where can I pass that information? Well, the arguments of the exec system call will include that the path to the new program that you want to execute from there on. All right. Now let's take a look at some examples. Hopefully over here you guys will be sort of getting more insight into how this fork system call is going to work. So the first example that we have is simply a fork, right? So this is only focusing on fork system call. The other one will be fork and exec. So we have a main function, right? So we have a main function over here that returns an integer data type. We come into the main function. The first instruction that we have is PID, which is the integer data type, equals fork. So right there, we are going to create a new process. But we are going to have two things to consider, right? So one is parent. Let me draw it over here. And we are also going to have child process over here. So I can label this maybe a child there and a parent over here. So what is going to happen next? Well, the parent is trying to execute this instruction while the child is also trying to execute that next instruction right after the fork system call. Remember, the return code is different in parent and child. The return code, which we are sort of capturing in the PID variable, it is going to be 0 for child. It is going to be non-zero for parent, non-zero integer, right? So now we are sort of at the same place, right? Both parent and child are trying to execute this if condition next. And they're both happening concurrently. Now let us look at it maybe in the view of a child. What is going to happen in the child process? Well, your child process will be here. It will do this. It will execute the if instruction. It will compare the return code with 0. Sure, that's exactly it. It will match it, right? PID equals 0 for child. So that indicates that it's a child process. So it will go into this if loop and say it will do this work, right? So do work is another function to which we are passing this child string literal, which is what? Which is right here, right? So there is a do work function written over here which has certain instructions, and we are passing child to that do work function. And after that is done, we will successfully exit out of the child process. You guys see that? So if PID is 0, we are going to do this work, pass child to this, and then execute whatever instructions happen over here, and then successfully terminate the program. Now, in the meanwhile, parent also was trying to do the same thing. So it checked for the PID, and it was not 0 here. For parent, it is going to be the process ID of the child process. So it is not going to be 0. So it's not going to enter this if loop. It's going to go down here, check for the other option. PID is not equal to 0, indicates a parent process. It will do some other work, right? So it'll do work while we are passing the string literal of parent. So we are passing parent to this particular function here in that case. And then we are waiting for the child to exit. Wait for the PID with 0. And then once we wait, and then we can return back. Right. So as you are going through these fork instructions, that's what you are trying to keep track of. One thing important to note is both are trying to execute the next instruction over here. Right. That's something that to keep track of. Usually the confusing part is that and the return code. All right, so that's as far as fork is concerned. Now let's take a look at fork plus execute, right? So this is creating a new process as well as replacing replacing the program in one of them. So we are trying to look at both of them. So we have a main function over here in which we are passing two arguments. One is argc and the other is argv. Argc is essentially being used to keep a count of the arguments, and argv is a one-dimensional vector of strings over here. Next, we go down into the main program. We have PID as an integer data type. We have args as a pointer variable to a character data type, which has two string literals. And then we go into fork, right? So we had a parent process, do some initialization, and then we have a fork system command. Once we have fork, again, we have a parent and we have a child. So we have a parent over here and we have a child over here. This is C, this is P, and they are both trying to execute this statement right there. Now let's take a look at what happens in the parent process, because that is sort of a very easy thing over here, right? So for a parent process, it is first checking for PID whether it is equal to 0 or not. Well, of course, we know it's a parent process, so PID is not going to be equal to 0. So we are going to go down here, else we are going to simply do a printf of not a problem, and that's it. You see that? So the parent process is simply going to go down, print not a problem, and terminate. That's it. Now, during this time, the child is also trying to do the same thing, but now it is going to first check PID equals 0 or not. Well, for child it is. So now it is going to be executing these commands. What are they? Well, first we are saying args of 0 is essentially a path to an executable, right? So a.out is simply your compiled output of your C compiler. And we are essentially giving a path to that executable. args1, the second input to your args, is a null pointer. So you've got a path and a null pointer to complete that, two arguments. That is what we are passing using this exec v system call. So what is going to happen is it is going to replace this program with whatever needs to get executed based on this a.out executable, and it is going, the child process is going to run that executable instead. So that's essentially how you can swap out a parent process with a new process and have the child do something else. All right, that is all I have for you guys in terms of discussion. I think you guys are ready for the activity. Stop recording.